Welcome to this explainer. I'm absolutely thrilled you're joining me today because, well, together we're going to decode the hidden architecture of the physical world. If you really look closely, the world around us is constantly shifting and transforming, often in completely invisible ways. So we're going to be playing chemical detective today, uncovering those hidden microscopic interactions. We'll be taking a comprehensive masterclass journey through the foundational concepts of chemistry, from decoding balanced reactions to visualizing classic lab experiments and figuring out how these tiny microscopic shifts impact our everyday lives. Let's get right into it.
Let's kick things off with a pretty fundamental question. How do you actually know when a chemical change has actually happened? How do we definitively prove that an invisible bond has broken and reformed at, say, a literal or metaphorical crime scene? We obviously can't just see individual atoms shifting around with the naked eye, right? So, what is the undeniable physical evidence that tells us the chemical bonds of a substance have completely broken down and formed into something entirely new?
Here is our investigation roadmap for today. First, spotting chemical clues. Second, the language of chemistry. Third, balancing the scales. Fourth, the usual suspects. Fifth, oxidation in real life. And finally, number 6, essential lab experiments. All right, part 1, spotting chemical clues. Let's learn how to identify those reactions. So, there are 4 vital clues we need to be on the lookout for. If you spot any of these happening, you've almost certainly witnessed a chemical reaction. First up, a change in state. Think solid reactants suddenly converting into gases, or a solid precipitate forming basically out of thin air. Second is a change in color. Just imagine dipping an iron nail into blue copper sulfate and watching the liquid shift right before your very eyes to a light green, absolutely wild. Third is the evolution of gas. This is when a reaction actively releases gas bubbles, fizzing and bubbling furiously. And fourth, a change in temperature. The environment might suddenly get intensely hot, releasing heat in an exothermic reaction. Picture a dazzling white flame. Or, actually, it might experience a sudden icy drop in heat during an endothermic reaction. These are our primary sensory clues.
Moving right along to part 2, the language of chemistry. It's time to learn how to write the official detective's report. Now, chemists don't just use standard English to write out their findings, because, well, it simply isn't precise enough. Take the word equation. Magnesium plus oxygen yields magnesium oxide. It gets the job done, sure, but it's kind of clunky, it's long-winded, and honestly, a bit of a nightmare if we're detailing complex, multi-step processes. But then, look at the skeletal or chemical equation. 2Mg solid plus O2 gas yields 2MgO solid. Wow! It's sleek, it's highly efficient, and it tells us precisely what atoms are involved, their exact quantities, and even their physical states. It is literally the ultimate shorthand for understanding these interactions.
Okay, part 3, balancing the scales, or as I like to call it, the mathematics of chemistry and the conservation of mass.
The absolutely crucial point to understand here is the law of conservation of mass. This is the golden rule of chemistry, guys. It states that mass can neither be created nor destroyed in a chemical reaction. Put simply, the total mass of your reactants absolutely must equal the total mass of your products. Think of it kind of like an accounting ledger at a highly secure bank. Every single atom that goes into a reaction on the left-hand side must eventually come out on the right-hand side. The atoms might swap partners, they might rearrange themselves into entirely new configurations, but the total count of each specific type of atom, that cannot change. No way. The books must balance perfectly.
So how do we actually balance that ledger? We follow an intuitive step-by-step puzzle. There are 4 unskippable steps here. Step 1, write down the skeletal equation and draw boxes around the chemical formulas. This is vital. You literally cannot alter anything inside those boxes. You can only put numbers in front of them. Step 2, list out the exact number of atoms of each element on both the left-hand side and the right-hand side. Step 3, start balancing. And actually, here's a quick pro tip to speed things up. Always start with the compound that contains the maximum number of atoms first, regardless of whether it's a reactant or a product. Trust me, it makes the math so much easier. Finally, step 4. Once the numbers match up perfectly, include the physical state symbols. S for solid, L for liquid, G for gas, and AQ for aqueous, which just means dissolved in water.
Part 4, the usual suspects. Let's round up the different types of reactions.
Our first 2 foundational reaction types are pretty much exact opposites of each other. First up, we have the combination reaction. This is where 2 or more reactants join forces to form a single unified product. A great example of this is quicklime reacting with water to form slaked lime, which releases an intense amount of heat in the process. They just combine, Conversely, we have the decomposition reaction. This is where a single complex molecule, our main suspect, if you will, breaks apart into multiple simpler pieces. Usually, this process requires some energy, like heating up ferrous sulfate crystals until they break down into completely new substances.
Now, things get slightly more complex with our next two suspects. In a displacement reaction, a more reactive, let's call it aggressive element, essentially kicks out a weaker, less reactive element from its solution and takes its place. Just think of iron kicking out the copper from a copper sulfate solution. But then we have the double displacement reaction. And this isn't just one element taking over. No, this is a full-blown, simultaneous swap of ions between two reactants. They completely trade partners, often forming what we call a precipitate, which is an insoluble solid that just suddenly drops out of the liquid mixture.
Which brings us to part 5, oxidation in real life. Let's look at redox reactions. The oxidation and reduction processes, which are commonly mashed together as redox, well, these two are partners in a chemical dance. One rarely happens without the other. A substance undergoes oxidation when it gains oxygen, loses hydrogen, or loses electrons. On the flip side, a substance undergoes reduction when it loses oxygen, gains hydrogen, or gains electrons. So they are constantly trading oxygen, hydrogen, or electrons back and forth. It's really a fascinating, continuous exchange.
Now, you might be wondering, why should I care about this abstract treating of electrons and oxygen? Well, because oxidation has incredibly relatable, real-world stakes. It is the exact process behind corrosion. That's when metals get attacked by moisture and acids, leading to surface degradation. Yep, it's the rust literally eating away at our cars and bridges. We have to actively prevent it through painting, oiling, or galvanization. And guess what? Oxidation is also the main culprit behind rancidity. When the fats and oils in our food oxidize, it causes that awful, unpleasant smell and foul taste that totally ruins our snacks. That's exactly why food packaging uses antioxidants, nitrogen gas flushing, and those airtight containers. We are basically in a constant, never-ending fight against oxidation.
Okay, part 6, essential lab experiments. Let's visualize this chemistry.
Let's quickly review the physical evidence from some classic laboratory setups to really lock in what we've learned today. First, the burning of a magnesium ribbon. If you've ever seen this in a lab, you know it produces a dazzling, blindingly white flame before turning into a white powder. Honestly, it's an unforgettable sight. Then there's the electrolysis of water, where we literally pull water apart using electricity. This produces a perfect 2-to-1 ratio of hydrogen gas to oxygen gas in our collection tubes. It is quite literally the law of conservation of mass playing out in visual form. Next, if you heat ferrous sulfate crystals, you don't just see the green crystals turn white and then reddish-brown. You are physically hit with the distinct, choking fumes of sulfur gases. And finally, mixing zinc granules with dilute acid, this evolves hydrogen gas bubbles, and the true test here is bringing a burning candle near the delivery tube just to hear that satisfying, sharp pop sound of the hydrogen igniting. Chemistry isn't just numbers on a page, guys. It is a deeply sensory experience.
So, we've explored the clues, we've learned the language, balanced the scales, and rounded up the foundational reactions of the chemical world. But you know what the most incredible part of understanding this architecture is? The reactions never actually end. From the slow rusting of an iron gate down the street to the complex digestion of the very last meal you ate, what unseen chemical equations are balancing inside you right now? The world is just a giant, endless chemistry lab. Keep your eyes open for the clues, and I'll see you in the next explainer.